Hello everyone! Our lesson for this week is titled Momentum and Impulse, Conservation of Momentum. Our objective is to relate impulse and momentum to collision of objects. Based on Newton's third law, for every action there is an equal and opposite reaction. When two billiard balls hit each other, they exert a force to each other of equal magnitude and opposite direction. We can derive the law of conservation of linear momentum from Newton's third law, wherein Fa and Fb are action-reaction pair from Newton's third law, which are equal in magnitude and opposite in direction. Object A exerts a force or impulse on object B, and object B exerts a force or impulse on object A. Mathematically, Newton's third law can be written using this equation, Fa is equal to negative Fb, to prove that they are equal in magnitude, opposite in direction. Since whenever there is force, there is also impulse in colliding objects, we can also rewrite Newton's third law using this equation. Ia is equivalent to negative Ib. And we know that I is equivalent to delta P, or change in momentum. Substituting the change in momentum to our equation, we can now have this equation for object A and object B in terms of change in momentum. Using the distributive property, we now have this equation. Since the change in momentum before collision is equivalent to the change in momentum after collision, we will combine all the momenta before collision and all the momenta after collision. We now have negative MA-UA minus MB-UB is equivalent to negative MA-VA minus MB-VB. Multiplying both sides by negative 1, we now have a final equation of MAUA plus MBUB is equivalent to MAVA plus MBVB. Take note that this equation is what we call the law of conservation of momentum. MAUA plus MBUB is equivalent to MAVA plus MBVB, wherein MA is the mass of object A, MB is the mass of object B, UA is the initial velocity of object A, UB is the initial velocity of object B, VA is the final velocity of object A, and VB is the final velocity of object B. Collisions are classified according to whether the kinetic energy changes during the collision. There are two types of collision, elastic and inelastic. In an elastic collision, the total kinetic energy of the system is the same before and after collision. While in a perfectly inelastic collision, the total kinetic energy is still conserved, but the two objects stick together and move with the same velocity. Thus, some of the kinetic energy is converted to heat. Here are the equations we will be using for elastic and inelastic collisions. Take note that you can solve for the final velocity of an object in elastic collisions for object A and object B. So, final velocity of A is equivalent to mb/UB all over ma, while the final velocity of object B is equivalent to ma/UA over mb. Now for inelastic collisions, since after collision they will stick together, they will have the same final velocity. Therefore, we can use this equation MAUA plus MBUB is equivalent to the quantity of MA plus MB times V. Let us have the sample problem. Two billiard balls collide in a perfectly elastic collision. Ball A has a mass of 0.8 kg and an initial velocity UA of 3 meters per second. Ball B has a mass of 0.3 kg and an initial velocity UB of negative 2 meters per second. Determine the velocity of each ball after the collision. Using our equation, VA is equal to MBUB all over MA, we can substitute the given quantities and get a final answer of negative 0.75 meter per second. While for VB, we will be using the equation MAUA over MB. And we get a final answer of 8 meter per second. Let us now have the second problem. Two clay objects collide in an inelastic collision. Object A has a mass of 0.8 kg and an initial velocity UA of 4 meters per second. Object B has a mass of 0.4 kg and an initial velocity UB of negative 2 meters per second. Determine the final velocity of A and B. Using our equation for inelastic collision, we now use MAUA plus MBUB is equivalent to quantity MA plus MB times V. Substituting our given quantities in the equation, we now have a final velocity of 2 meters per second. Now let us try to determine the kinetic energy before and after collision in this given problem. Two identical billiard balls with a mass of 2.0 kg collide in a perfectly elastic collision with a speed of 4 meters per second. After collision, they moved with a speed of 4 meters per second in the opposite direction. Determine the kinetic energy before and after collision. When you were in grade 8, we discussed that the kinetic energy can be computed using the equation 1/2 mv squared, wherein m is the mass and v is the speed or the velocity. So kinetic energy before is equivalent to kinetic energy after. Using the equation 1/2 ma ua squared plus 1/2 mb ub squared is equivalent to 1/2 ma va squared plus 1/2 mb vb squared. We can substitute the given quantities and arrive at a final answer of 32 kilogram meter squared per second squared is equivalent to 32 kilogram meter squared per second squared. Since the kinetic energy before collision is equivalent to the kinetic energy after collision, we can say that kinetic energy is conserved. Now let us have this problem. Two clay balls, a mass of 0.8 kg with a velocity of 4 meters per second, and a 0.4 kg with a velocity of 2 meters per second collide in a perfectly inelastic collision. After collision, they moved with a speed of 2 meters per second. Determine the kinetic energy before and after collision. Using our equation for kinetic energy before is equal to kinetic energy after collision and substituting the given quantities, we were able to compute that the kinetic energy before is 7.2 kg meter squared per second squared and the kinetic energy after is 2.4 kg meter squared per second squared. The kinetic energy before is not equal to the kinetic energy after. So in order to identify the kinetic energy converted to heat, we get the difference between the values of the kinetic energy before and kinetic energy after collision, and the value is 4.8 kg meter squared per second squared. This means that some of the kinetic energy is converted to heat. In other words, kinetic energy was reduced to 33% or one-third. Take note that even if the kinetic energy in the problem is reduced to 33% or one-third, the momentum of the system is still conserved. We can verify that using the law of conservation of momentum equation, substituting our given quantities, and we can still get a momentum of 2.4 Newton second before and a momentum of 2.4 Newton second after collision. So we can say that even if the kinetic energy is converted to heat, momentum is still conserved.